Thank you very much. So I'm extremely grateful to the organizers, to Lionel, Lucrezia, David, and Petra for the kind invitation, for the opportunity to speak here. This is truly a great, great pleasure and honor for me to participate in this wonderful conference. And actually, in this talk, I would like to speak a little bit about some recent observations concerning semi-classical analysis for some classes of non-self-adjoint operators arising in condensed matter physics of two-dimensional materials. And the new results that I would like to discuss are actually joint work with Maciej Zworski. So in this talk, we are going to be concerned with the so-called twisted bilayer graphene, and I would like to start just by saying a couple of words concerning the physical background, just in a very sort of naive and superficial way describe the, the corresponding underlying physics, which only reflects my own very primitive level of understanding of the physical phenomena behind this. So basically what you do is that you start with a single sheet of graphene, which is a two-dimensional honeycomb arrangement of carbon atoms, and then on top of this sheet, you put another sheet of graphene with a small relative twist. And then what emerges in this situation is a so-called Moiré pattern, which basically means that you're in the presence of a new periodic or quasi-periodic structure, but at a much larger length scale. So the size of the fundamental cell is much larger, and that actually leads to certain two-dimensional materials which display some unusual and occasionally striking electronic properties, including actually superconductivity, provided that the twisting angle has been suitably chosen. So this has been experimentally observed relatively recently by several groups. And actually this confirms a theoretical prediction that was made by Bistrica and McDonald that you should be observing superconductivity in such a twisted bilayer graphene configuration some 12, 13 years ago. So in this talk, from the mathematical point of view, we are going to be looking at a so-called chiral limit or chiral model for twisted bilayer graphene. And as we shall see, this particular model seems to be the one which has the nicest mathematical properties. So we shall concentrate on some of mathematical aspects of the twisted bilayer graphene Hamiltonian in the chiral limit. This particular chiral limit was considered first in a fairly recent paper by three physicists, Napolsky, Kryuchkov, and Vishwanath. And actually, I should say that this Hamiltonian is obtained from the full Bistrica-McDonald Hamiltonian by suppressing certain tunneling interactions between the two sheets. So from the mathematical point of view, what we have is the following nice self-adjoint Hamiltonian, H of alpha. As you can see, it is a system. It is a 4x4 first-order system acting on functions on the plane. So it will be convenient for me to use the complex notation for the complex variable z in the complex plane, x1 plus ix2. And the structure of the self-adjoint Hamiltonian is the following. I have the zeros along the diagonal. That reflects the chiral symmetry of the model. And then off diagonally, I have a certain operator, d of alpha, in the lower left-hand corner, and its adjoint in the upper right-hand corner. And this non-self-adjoint operator, d of alpha, is a 2x2 first-order system. So as you can see, it is non-self-adjoint. And the structure of this non-self-adjoint operator is the following. Very nice looking operator. You basically have the Cauchy-Riemann derivative along the diagonal, which we cosmetically multiply by 2 over I. And then off diagonal, you have a certain potential, u of z, u of minus z, which is a completely explicit potential coming from physics, the so-called Bistrica-McDonald potential, which is being multiplied by a dimensionless coupling constant alpha. So in this talk, eventually, we are going to be sending actually alpha to infinity, and this will be regarded as the semi-classical limit for our twisted bilayer graphene Hamiltonian. So the physical significance of alpha is that it is inversely proportional to the twisting angle. So from this point of view, sending alpha to infinity and considering the semi-classical limit for this Hamiltonian corresponds to the small angle limit problem. Okay, so this Bistrica-McDonald potential is an absolutely explicit thing. Here it is. It is expressed in terms of this parameter capital K. Omega here is the cubic root of unity. And then I have this bracket notation just for the ordinary scalar product of vectors in the plane, which we describe using the complex notation. So as you can see, this potential is certainly real analytic, and this aspect will be important a little bit later. So that's the Hamiltonian that we consider. So I should say that this Hamiltonian and the full Bistrica-McDonald Hamiltonian was introduced in particular by Bistrica and McDonald purely empirically But more recently, there have been some rigorous mathematical works, in particular by Kansas and collaborators, and Watson, Kong, MacDonald, and Luskin, where this Hamiltonian has been derived from some ab initio, models in physics. But for us, we're just going to approach this from a pure sort of PDE point of view and try to study some of the mathematical properties of this Hamiltonian. And so with this in mind, let me introduce the following nice lattice in the plane, capital lambda, the so-called Moiré lattice. And then associated to this lattice, I also have the dual lattice lambda star. And then what is nice is that my Bistritzer-McDonald potential has certain symmetries with respect to the Moiré lattice. In particular, I have this nice Flaquet periodicity condition. So if I translate my Z by an element of the lattice lambda, then I pick up this, Flaquet factor. So I have this periodicity, Flaquet periodicity condition. There's also this rotation symmetry. If I rotate Z, I rotate the potential, and a certain reality condition that this potential U enjoys. So in particular, the first property tells me that if I replace my lambda by a larger lattice, multiplying lambda by a factor of 3, actually, then because of this expression for capital K, I conclude that my potential is actually periodic with respect to this larger lattice. So as a matter of fact, this Hamiltonian that we're concerned with is a periodic Hamiltonian, which we usually encounter when studying condensed matter physics. And so one sort of striking aspect, and maybe the first manifestation of the fact that this chiral model is nice from the mathematical point of view, is that from the spectral theory point of view, this chiral model enjoys this nice phenomenon of having flat bands. So I will say one word about that. It will play a certain role in what follows. So basically what you would like to do, you would like to develop some kind of spectral analysis for your self-adjoint operator H of alpha, which is periodic. And then what we usually do in such a situation is that we do some kind of Flaquet reduction, where we pass from our self-adjoint periodic Hamiltonian on all of the complex plane to a family of self-adjoint operators acting on a torus. And in this case, it is completely explicit. We basically just conjugate our self-adjoint operator H of alpha by this linear exponential weight. We introduce the quasi-momentum K, which varies in this dual torus, gamma, or maybe just in the complex plane, actually. Gamma star is the dual lattice to the periodicity lattice. And then you can see that this conjugated operator, because H of alpha was the first order, basically looks like this. Okay, so you have D of alpha being replaced by D of alpha minus K, and likewise here you replace D of alpha adjoint by D of alpha adjoint minus the complex conjugate. So now you have a family of self-adjoint operators parametrized by the quasi-momentum. They act on the torus. So these are self-adjoint operators which have discrete spectra. And so by definition, we say that a flat band at zero energy occurs for my self-adjoint periodic Hamiltonian H of alpha if each of these self-adjoint Hamiltonians acting on the torus has 0 in the spectrum for every value of K. So you see from this explicit description that in order for 0 to be an eigenvalue of such a self-adjoint operator, it basically means that this operator that we see in the lower left-hand corner here, D of alpha minus K, should develop some non-trivial kernel for every value of K. And so a flat band at 0 energy for the self-adjoint Hamiltonian H of alpha occurs precisely when the spectrum of this non-self-adjoint operator D of alpha acting on the torus is the entire complex plane. Okay? So this is a little bit peculiar from the spectral theoretic point of view. After all, D of alpha acting on the torus is a very nice elliptic operator. It acts on a compact manifold. So how can such a thing even occur? But of course, this is a non-self-adjoint operator. So from the general spectral theory point of view, we know that there is a basic dichotomy. If you have an elliptic operator of positive order acting on a compact manifold, which is non-self-adjoint, then its spectrum is either discrete, possibly empty, or it could be the entire complex plane. And actually, this phenomenon, when the spectrum fills out the entire complex plane, received in this particular case corresponds to this phenomenon of having flat bands, which is supposed to be related to superconductivity. Not really mathematically well understood, but this is what we can take from this discussion. So this is just a general remarks, but the particular situation in the case of the Bistritzer-McDonald potential and the situation with flat bands has been greatly clarified in this nice paper by Becker, Embry, Wheatstone, and Zworsky a couple of years ago. So what they proved is that there exists a discrete set of parameters in the complex plane, capital A, such that when our coupling constant alpha avoids this set, then the spectrum of this non-self-adjoint operator is actually discrete, and it is equal to the dual lattice. This is exactly what you would get if alpha had been equal to 0. You just get the d-bar operator with periodic boundary conditions. The spectrum becomes exactly the dual lattice. Otherwise, when alpha belongs to this discrete set, the spectrum becomes the entire complex plane. So you have this somewhat, unusual situation where you're varying alpha. Occasionally, you will hit upon elements of this discrete set, and then your spectrum turns from being a lattice to becoming the entire complex plane. So physicists are talking about magic angles as being those angles for which superconductivity occurs. If we think about, the flat band phenomenon as corresponding to superconductivity, then we can say that elements of the reciprocal set 1 over alpha, when alpha varies over this set, these are the magic angles, and we can think about this set, discrete set A, as some kind of a magic set. Okay, so I won't say too much about the proof of this result, but one aspect of the proof that I will actually use in what follows is it turns out that the symmetries of the potential that we reviewed in the beginning of the talk actually protect the kernel of my non-self-adjoint operator, and you can actually show that this operator develops a non-trivial kernel for all the values of alpha in the complex plane. And then this is the purely consequence of the symmetry considerations. And then you can combine this fact with some basic functional analysis, and this is how this theorem is proved, at least in the original paper by Becker, Embry, Whitson, and Zworsky. There was also a nice recent paper by Galkovsky and Zworsky, which introduces a more abstract approach to the flat band condition, which applies in some other situations not covered by, by this example. And I shall actually return at the very end of the talk to this paper and mention something else about it. So here is a numerical picture of this discrete set, which comes from the same paper by Becker, Embry, Whitson, and Zworsky. So this, as you can see, this is a set which enjoys certain symmetries in the complex plane. Points, these red dots here correspond to elements in the set which are real and positive. So these are presumably physically relevant reciprocals of magic angles. But basically, the mathematical structure of this set is not really understood. I would only like to mention 2 rigorous results of which I'm aware concerning the structure of this set. One of these results is due to Becker, Humbert, and Zworsky in a follow-up paper where they show that the set is infinite using fairly ingenious trace computation argument. And then there is a same paper by Becker, Humbert, and Zworsky, and then in a parallel paper by Luskin and Watson, actually that the existence of a first real positive magic alpha has been demonstrated. So this corresponds to the first red dot right here. So before, we're still kind of motivating a little bit this setting of twisted bilayer graphene, and I would just like to mention that there is sort of a tantalizing and striking numerical observation that was first done in the physics paper by Ternapovsky, Kryuchkov, and Vishwanath, and then confirmed with a greater numerical precision in the paper by Becker, Embry, Whitson, and Zworsky, is that it seems that the elements in this discrete set A that are real and positive, they seem to obey some kind of quantization condition, is that they seem to be evenly spaced. Ideally, this should be, observed in the limit of large alpha. So the spacing being roughly 3/2, or more precisely 1.515. So I'm only mentioning it because starting with the pioneering work by Melin and Sjöstrand done more than 20 years ago, there has been several works where so you think about some kind of quantization condition corresponding to this equidistant spacing. And so what I would like to point out is that there have been several works where a Bohr-Sommerfeld quantization condition has been justified for various classes of non-self-adjoint operators in dimension 2 in the presence of analyticity and also in the semi-classical limit. So this was first done by Melin and Sjöstrand in their pioneering paper, and then with Johannes Sjöstrand we have been investigating various, and actually also with some, we have been investigating various classes of non-self-adjoint operators in dimension 2, for which you can describe eigenvalues using some kind of a 2-dimensional Bohr-Sommerfeld rule, and you observe certain lattices of eigenvalues. So I'm only mentioning it because this particular problem of twisted bilayer graphene seems to share all of the features that were present in those previous works. It is a 2-dimensional problem which is non-self-adjoint. We are in the presence of analyticity, and we are going to be looking at this problem in the semi-classical limit. So it would be very nice to try and bring some of those techniques to bear on this particular problem. We haven't yet been successful in doing that, but this remains sort of an interesting and open problem, from the rigorous point of view to apply this 2-dimensional machinery. Okay, and so maybe my last slide to motivate the problem a little bit is the following. So we saw that this non-self-adjoint 2x2 system, d of alpha, has this unusual spectral property of basically switching from a discrete set, as far as the spectrum is concerned, to the entire complex plane. Well, actually, there has been a little bit of a tradition of looking at non-self-adjoint operators whose spectra exhibit this kind of unusual behavior. And actually, in this paper by Melin and Sjostrom that we just reviewed, somewhere in this paper, the authors consider the corresponding, similarly looking operator also acting on the torus, but which is scalar. So for scalar first-order operators that are elliptic, situation somehow is much more clear. You can consider an operator of this kind, acting on the torus, not unlike the torus that we saw previously. A and B are smooth coefficients, A nowhere vanishing, so it's an elliptic first-order operator. And then you can actually understand the spectrum of this operator quite explicitly acting on the torus just by analyzing the problem on the level of Fourier series. So you find an explicit condition for lambda to be in the spectrum in terms of certain averages of the coefficient B over A and then 1 over A. Gamma star, as before, is the dual lattice. So most of the time you get a lattice of eigenvalues, but actually if this coefficient were to be equal to 0, then the spectrum becomes either the entire complex plane or empty set, depending on whether or not this particular coefficient belongs to the dual lattice. So this is a two-dimensional example on a two-dimensional torus, and actually there was a predecessor to this paper, a very nice short paper by Robert Seeley from 1986, which essentially makes the same point of an example of a first-order elliptic operator just on the circle, where the spectrum is basically either empty or the entire complex plane. So it is this particular operator that Seeley considers. And actually, the title of Seeley's paper, if I remember correctly, goes along the line of something like, pathological spectral behavior for non-self-adjoint operators. But here we see that this behavior is not really so pathological. It actually comes from a physically significant problem. And this phenomenon of the spectrum being the entire complex plane has some real physical significance. Okay. So I would like to focus now on the main part of my talk, which is going to be the following. We're going to be considering the semi-classical limit for twisted bilayer graphene. Remember, that means that we are going to be sending our parameter alpha to infinity. So we're going to be looking at alpha large and positive. And actually here it won't matter. So my alpha will just go to infinity within or without the magic set. This will be the semi-classical limit, and then what we would like to do, we would like to understand the structure, semi-classical structure of null solutions to this non-self-adjoint problem, and try to relate this structure to some kind of symplectic or classical properties underlying this operator. This is usually what we try to do in semi-classical analysis. And so the first thing we do, we reformulate this problem in a convenient semi-classical way. So we introduce a small parameter h, which is just 1 over alpha, so we can treat this problem using traditional semi-classical approach. We cosmetically multiply this equation by h, and then we can rewrite this problem in a more traditional semi-classical notation. We introduce this nice semi-classical operator little p, which is just the same thing as before, but multiplied by h. But now I have my differentiation coming with a factor of h in front. And this is my system, and I can think about this thing as the quantization of this particular matrix-valued system, little p. As you can see here, when describing this little p, I'm using the complex notation z that we introduced before, and also the zeta is 1/2 xi1 minus I xi2. Xij is the dual variable to xj, and it is convenient to include this factor 1/2. We shall see later on why this is so. So this is the kind of problem that I would like to consider. It is a system, first order 2x2 system. And actually, we would like to understand the behavior of null solutions as h becomes small. So one simple reduction that we can make at this point is the following. It's a simple-looking system, but nevertheless, it is a system. And we would like to work as closely as, try to get as closely as possible to the scalar problem. So what we do is some kind of a principally scalar reduction, which is very easy in this case because we're interested in null solutions. So what we do, we just compose this system, first-order system, with the adjugate matrix by putting it to the left. And then what happens is that you get a principally scalar system in the sense that the principal part of this new operator is going to be scalar. It is going to be given by the quantization, which I'm denoting by a little q of x h dx. And the the corresponding symbol here, little q, is nothing else but just the determinant of little p that we introduced on the previous slide. So as you can see, the corresponding quantization looks like this. It's basically d bar squared, also semi-classical d bar squared, and then I have a certain complex potential, u of z being my explicit Bistritzer-MacDonald potential. I also have a sub-principal term here, which is matrix valued. In fact, this matrix R of x is a very nice zeroth order matrix, and then it is being multiplied by some semi-classical parameter h. So for our purposes, we're actually going to be able to neglect this until the very end of the talk and concentrate on properties of the principal symbol little q here. So rather than looking at the previous problem, we're going to be looking at null solutions to this principally scalar system, just to be able to work with methods that really come from scalar techniques. And now, let's take a look at the following two pictures. So maybe we start with the picture on the left. So the picture on the left depicts the following situation. What you have in black here is a fundamental domain of the Moiré lattice. Inside of this fundamental domain, you have two distinguished points, non-zero points, that are so-called stacking points in the physics literature. And these are non-zero points of high symmetry with respect to the action of the multiplication by cubic root of unity. They're just given by plus minus I over square root of 3. And then these two stacking points, together with the lattice, I should say, generate a certain hexagon. So you have one vertex of the hexagon here, and then you have another here and another here, corresponding to the lattice, and then you have minus the stacking point here, and then you have another vertex here and another vertex here. So this is the hexagon that we can draw in the z-plane associated to the stacking points and the lattice lambda. And what you have on the right actually is a numerical picture, which comes from the same paper by Becker, Embry, Whiston, and Zworsky. And what is being depicted here is the log plot of the absolute value of a null solution of an element of the kernel of our non-self-adjoint operator d of alpha, alpha being moderately large, 11.345. So what we see here in the picture is that the dark blue color corresponds to u being very small, as a matter of fact, exponentially small as alpha gets large, and then the yellow color corresponds to u being roughly 1. So what seems to be happening, at least in this numerical picture, is that our solution seems to be getting very small, actually exponentially small as alpha increases, around the hexagon corresponding to the picture on the left, and actually also, as you can see, in the center of this hexagon. So we would like to understand a little bit this phenomenon of decay of these eigenfunctions, and thinking about the usual terminology coming from elementary quantum mechanics, we can say that here we seem to be in the presence of a classically forbidden region, in the sense that it is in this region, close to the hexagon, that our eigenfunction exhibits some exponential decay properties. Okay. So to be able to appreciate the significance of this hexagon a little bit more from the point of view of the corresponding classical picture, let's take a look at another plot. And what is being plotted this time is actually the Poisson bracket of the principal symbol little q that we introduced earlier. Actually, here it is, as you can see. So it's a complex valued function. And what we can do, we can compute the Poisson bracket of q and q bar. And then we can restrict this thing to the energy surface q equals 0. And then we get a function which can naturally be regarded as a function of the base variable z. So the formula for the Poisson bracket actually will appear a little bit later in this talk towards the end, but we can just keep in mind that we can think about the Poisson bracket as basically measuring the extent to which our operator fails to be self-adjoint from the classical point of view. It's the classical analog of the commutator. So what is interesting in this picture actually is to consider the curve or the set in red, because the set in red here corresponds exactly to places where the bracket is equal to 0. So what we see here is that actually the bracket vanishes exactly on the hexagon that we introduced on the previous slide, and actually it also vanishes on the center. This second picture to the right is basically the same picture, which is now being drawn over a fundamental domain over a larger lattice, the periodicity lattice. So we see this periodic pattern repeating itself. But basically, having seen these pictures, we seem to be in the presence of a phenomenon where there has to be some link between the geometry of the region where the Poisson bracket vanishes and exponential decay of solutions to our principally scalar system coming from twisted bilayer graphene. Okay, so before I state the main result of this talk, I would like to recall the situation concerning classically forbidden region in the familiar case of semi-classical Schrödinger operators. So if you have such a nice semi-classical Schrödinger operator and you work at some energy level E, let's say V is a nice confining potential, then it is well known that in the semi-classical limit, your normalized eigenfunction U is going to exhibit some exponential decay in the classically forbidden region. And the classically forbidden region for such an operator is exactly the region where the values of V exceed the energy level at which we work. And we can actually understand this phenomenon of exponential decay in this particular case as a consequence of the fact that in the classically forbidden region, our operator is elliptic. Because if you consider the symbol of the semi-classical Schrödinger operator, here it is, then whenever x0 is in the classically forbidden region and psi is any real takes any real value of the momentum variable, well, it's non-zero, which means that you have good a priori estimates in L2 for this operator, and you can develop some method of conjugations by exponential weight and conclude that your eigenfunction has to decay exponentially. And this, of course, goes back to classical ideas of Agmont, Simon, and in particular the semi-classical point of view was emphasized in the celebrated work by Alfer and Sjöstrand. So if we were to compare this well-understood Schrödinger picture with the corresponding situation for twisted bilayer graphene, then we see that we cannot really argue on the level of ellipticity when trying to justify the exponential decay of our eigenstates in the semi-classical limit, because our symbol compared with this little p, this little q, is now complex valued, and there are really no classically forbidden regions for this guy here in the sense of ellipticity, because no matter what z or no matter what x0 I fix in the plane, then there will always be some zeta for which this thing is going to be equal to 0. So the fiber above this point x0 will necessarily hit the energy surface q equals 0. I just cannot help it. So therefore, I cannot really conclude the exponential decay of these eigenstates by ellipticity considerations alone. So the idea is now to try and replace ellipticity by some kind of hypoellipticity. And since we are thinking about exponential decay, or we would like to prove exponential decay for these eigenstates, we would like to be thinking in terms of analytic hypoellipticity replacing ellipticity. Okay, so now I think I'd like to state the main result. So one more time, this is the link that we are trying to establish. We are trying to establish the link between the geometry of the region where the bracket is equal to 0, so this hexagon, and on the other hand, we would like to relate the geometry of the region where the bracket is equal to 0 to the exponential decay of null solutions to this principally scalar system. Okay, so now comes the main theorem that we proved with Maciek-Zworsky at the end of last year. And as you can see, it's a theorem which has sort of a general nature. So probably in the remaining 5 to 6 minutes, I'll state the theorem, and then we'll just apply this theorem to twisted bilayer graphene to see what it gives actually in the case that we started with. But the theorem itself is a little bit more general. It is a local result. So in the sense that we work on some open set in the plane, and then we consider a principally scalar system, not unlike the one that we saw in our discussion of twisted bilayer graphene. So the principal part is a certain semi-classical differential operator of order 2, just like what we saw in our twisted bilayer graphene application. It's a scalar operator. You have some sub-principal term. It could be some first-order operators, even though in our case these are zeroth-order operators. This is the sub-principal term, which is matrix valued. What is important is that the coefficients of capital Q and of all of these entries in the sub-principal part are real analytic in the open set U. And then you have the following situation. You fix some point x0 in the open set, and you assume that at each point in the characteristic surface q equals 0 intersected with the fiber above x0, the bracket vanishes. This is what we saw happen along this hexagon. The bracket was equal to 0. And then you require that the second bracket evaluated at each point of this set should be different from 0. You should also demand that there should be some linear independence condition for the Hamilton vector fields of Q and Q bar. And then the conclusion is that if you consider a null solution of your principally scalar system in that open set, whose behavior as h goes to 0 is reasonable in the sense that the L2 norm stays, let's say, uniformly bounded, then there has to be a sufficiently small but fixed neighborhood of x0 in which our solution decays exponentially. So we can say that a neighborhood of x0 is a classically forbidden region for this principally scalar system in the sense that exponential decay occurs inside of this neighborhood as a consequence of these purely classical conditions involving the Poisson brackets for the principal part or principal symbol of our principally scalar system. Okay, so this is basically the phenomenon of exponential decay is being caused by these bracket conditions. Okay. So maybe I'll have time just for a very quick and elementary example, just to get a little bit of feeling for this. You know, somebody told me once that whenever you are giving a talk, you should always prove something during the talk. Then it instills a sense of security in the audience. So hopefully this will do it. I mean, it could be a false sense of security, of course, but nevertheless. So let's take a look at a very simple example in dimension 1, where we're just looking at the scalar operator, and my symbol little q is just this, okay, xi plus ix squared, we're working near the origin, and then psi is also have to be equal to 0. You compute the first Poisson bracket at 0, the second Poisson bracket is not equal to 0, so the conditions in the theorem are satisfied. And then what is nice about this one-dimensional example is that we can actually solve the corresponding equation and compute all the null solutions here, because it just amounts to a first-order linear ODE. So we use the method of integrating factor, and we find this particular expression for the solution. So now you see this factor here, e to the x cubed over h, is going to exhibit some exponential growth for x positive for sure. But of course, remember, we are assuming that the L2 norm over a fixed neighborhood of the origin is uniformly bounded. That can only occur when the initial condition for my solution is exponentially small. But then, of course, if this is exponentially small, then the whole thing is exponentially small in a smaller neighborhood of 0. So this is a very sort of elementary example which doesn't really do justice to the theorem, but at least it indicates that when we are under the bracket assumptions and we have some initial, tempered condition concerning our null solution, it has to be exponentially small. Basically, if it is not exponentially large, it has to be exponentially small. Okay, so let me finish by applying this theorem to the chiral model. So in the chiral model, this is the principally scalar system that we are considering. This is the principal symbol of the chiral model. And then we are using this complex notation. And then what is nice about this complex notation is that both the symplectic structure on the phase space and the Poisson bracket, that's actually the expression for the Poisson bracket that we were using in the computation, they receive some nice form. So actually all we have to do to apply the theorem is just to compute two Poisson brackets and make sure that the first bracket vanishes, and then the second bracket does not vanish. And then we are going to be able to conclude that our solution decays exponentially near a certain point. So you do that. Remember that this potential U is an absolutely explicit thing. We introduced it in the very beginning, the Bistritzer-McDonald potential. So the computation of the first bracket is fairly straightforward. This is the corresponding expression that you get for the bracket. So essentially, it is a matter of high school trigonometry to check that this thing actually is equal to 0 as you move over your hexagon. This is the picture that we recognized from before. It has been rotated 90 degrees. So you check that the first bracket is 0 everywhere, and it's an elementary thing to do. But already the computation for the second bracket is a little bit more involved. So you work it out analytically, you get a certain expression of this kind. This v of z is u of z times u of minus z. And so it's not obvious that you should be able to understand that this is not vanishing analytically. So first, actually, we did it numerically. But actually, somewhat miraculously, because of some nice features of the chiral model, you can actually do that. You can do the computation purely analytically. And then you find that the second bracket is non-vanishing as long as you stay away from the corners of the hexagon. Okay, so actually this computation breaks down at the corners of the hexagon in the sense that this thing is actually equal to 0. But if your point is away from the corners, if it varies on an open edge of the hexagon, then actually it works, and the theorem does apply to any point on an open edge of the hexagon. So finally, I will just like to say one word about what happens at the corners. So at the corners, our theorem does not apply because the second bracket actually is 0. So what can we say about the corners? Well, let's think about one of the corners. Maybe this is corresponding to the stacking point or minus the stacking point. The second bracket is not equal to 0, is equal to 0. So you continue computing higher order brackets, and you find that the first non-vanishing bracket that occurs actually corresponds to this one. You have to apply the Hamilton vector field of Q to Q bar as many as 4 times. So here actually we could not really find any theorem, or could not prove actually any theorem that would allow us to conclude exponential decay from this higher order bracket that was non-vanishing. But actually, nevertheless, Maciek-Zworski and his student, Jean Kaitao, were able to treat the case of the corners, not from the point of view of some general theorem about Poisson brackets, but just by using some ad hoc methods based on the specific structure of the principal symbol in a neighborhood of the corner. And as a result, actually, they were able to prove that a certain microlocal analytic regularity holds also at the corner, and actually exponential decay holds also near the corners. And I would just like to mention that my student, Reed Johnson, recently made some preliminary observations, but only in dimension 1, that somehow allow you to conclude that you have analytic regularity from some bracket conditions. And as we saw, that the dimension 1 is the case when you can really do explicit computations in this example. So finally, you get a theorem, which is joint work with Maciek-Zworski and his student Jean Kaitao, where we're able to conclude that given such a null solution of this non-self-adjoint operator, coming from twisted bilayer graphene, it has to decay exponentially in a sufficiently small but fixed neighborhood of the entire hexagon. These two observations cover the entire hexagon, and so there is a sufficiently small but fixed neighborhood in which our solution decays exponentially. And so my final comment concerns the following thing. If you remember, I mentioned that the bracket was not just vanishing on the hexagon, but it is also vanishing at the center of the hexagon, which was an isolated point. So what about the center of the hexagon? Well, the center of the hexagon is a very different story, it turns out, because my operator stops being of principal type. And actually, the symbol vanishes to the second order at the origin. And then in this case, whenever you are in presence of such a doubly characteristic point, you expect that the low-order terms should play a role. The sub-principal term that we have written down, but then it never really was causing any trouble, is now going to become essential. And this is seen very strikingly numerically, because this is the numerical picture of decay of solutions for the chiral model, where the sub-principal term is present. If we were to drop this sub-principal term entirely and consider the corresponding scalar problem, then numerically it seems that there is no exponential decay at the center of the hexagon. So the presence of the lower term really is a crucial aspect of the exponential decay at the center, and exactly how that occurs is not particularly clear to us. So it would be nice to figure it out as well. So I should probably stop here. Thank you very much for your attention. Thank you.
Do you have a sense in which this connects back to the magic angle stuff? So
this analysis actually completely disregards the magic angle structure of the problem. Yeah. So of course, what you can say in terms of the corresponding theorem on the torus is that here we are looking at this particular equation where you also have this k. So of course, in order to have a non-trivial solution for every k, this will occur precisely when alpha is a magic angle. On the other hand, if alpha is not a magic angle, then this is only, this is only significant when k varies over the dual lattice. Yeah. But you can say the theorem in this way for every alpha. Yeah. Thank you.
Other questions? Yes.
Sorry, do you have intuition why this second person bracket vanishes exactly at the
at the corner?
At the corners.
Well, this is a point of higher symmetry, so maybe that's not a very good explanation. But I mean, you expect something to go wrong at the corner, right? I'm sorry? Because of the geometry, yes. Yes, exactly. At first, we even thought that, we made some preliminary computation where it seemed that all the brackets were vanishing at the corner, but fortunately, that's not the case.
Maybe just a question concerning these slides. Do you expect that if you have some higher order Poisson bracket which vanishes, then there is exponential decay?
So ideally there should be a theorem, hopefully, which will tell you that if the first non-vanishing bracket, and this is what seems to be happening in the elementary one-dimensional case, that if the first non-vanishing bracket corresponds to this k being even, for example 2, 4 or something, then you should have exponential decay, roughly. That's the hope.
Other questions? Yes.
Okay, so I'm just wondering what is the operator d alpha?
Yes.
I didn't see it somewhere.
Let's go back to d alpha. This operator, right?
Okay. So what kind of symmetry we have in U? Is it a periodic somewhere?
So the symmetry of U, so here are the basic symmetries of U that, for example, go into the proof of the fact that there is a discrete set of parameters for which the spectrum becomes the entire complex plane. So all these symmetries are important, in fact. You need both the translation symmetry and you need both the rotation symmetry for that argument, I think.
Okay, well,
Please.
your last questions?
So in your picture,
Yes.
so you show the hexagon, but
Yes.
inside you also have this circular shape.
Yes, kind of circular.
This picture?
Yes, for instance, but also
You
the
mean the numerical picture?
yeah, also the last one where yes, so you have this circle here of yellow. So
Yes.
what is the explanation for this?
It's not. That's a very good question, and actually, it's not absolutely clear to us
Because on
what
the
happens.
left-hand side, you clearly see some quantization with
Yes.
respect to the Poisson bracket, which has to be sub-principal, right? Because
Yes. So it's actually, to be quite honest, what happens away from the hexagon is not particularly clear to us. Yeah.
it's probably related to your question about the Bohr-Sommerfeld
Yes,
interpretation.
probably. And actually, I should say, maybe I didn't mention it because I was in a hurry, but actually there is a very nice recent paper by Schostand and Vogel, and actually with Schostand and Vogel we now have some work in progress which concerns the general problem of tunneling for non-self-adjoint operators, of which this is not really a problem of tunneling, but we are observing some kind of exponential decay of solutions to a non-self-adjoint problem. So if one understands tunneling in a little bit more systematic way, then maybe one can understand this picture a little bit better. So what happens in this original paper and in our work in progress is that we're considering a very simple model situation, but it has some d-bar in it, so it's not completely unrelated to the twisted bilayer graphene. And so my personal hope that if we understand this model operator a little bit better, then maybe we can say something about tunneling also for the twisted bilayer graphene. But this is still open. Yeah. Thank you.
Okay, let's thank the speaker again.